If you remember that we have been talking about the S matrix, and we have written in terms of the reflection and the transmission coefficients, and this was actually written as R T prime and T R prime, where R prime and R and T prime and T are the reflection and the transmission coefficients corresponding to the left edge and the right edge of the system, which are connected to the system is connected to leads. So one corresponds to the left lead and the other corresponds to the right lead. I sort of wanted to give you a little more information on this S matrix, and let us just try to understand this from a purely quantum mechanical point of view. So let us think of a potential, okay, and the potential is given by V of x, and you have an amplitude going inward, which is A, and there's an amplitude going outward, which is B, and similarly on the other side there are outgoing amplitude going as C. These are the amplitudes of the waves, and this is again which is inward, that is moving towards the left, which is given by D. Okay, so for a closed system, which means that it is not connected to the surrounding, and in more technical terms it means that it's not a dissipative system, it's not connected to a bath, we can assume that V of x is real. Okay, it's a real function, and in which case S is a unitary matrix. Okay, and the unitarity condition is represented by this, where S dagger S is equal to a unit matrix, and the unit matrix, suppose I write a unit matrix in a 2 by 2 unit matrix, then it should be 1 0 and 0 1. Okay, in 3 by 3 it will just go up in dimensions. So you consider a scattering region, and the wave functions are represented by their amplitudes A, B, C, and D, which are respectively moving towards their directions in which they are shown. And I can write down a transmitted wave, let's call it as a transmitted, which is equal to the S, which is the S matrix of the incident wave. And this has been told that this is how the transmitted wave function is connected to the incident wave function, and we can write this as B, C, which are respectively, these are reflected and the transmitted waves, and these are S11, S12, S21, S22, and and these are A and D. So the B and C, let me write it the way I wrote here inside a square bracket. So this is the way this, so B and C, just to reiterate, these are outgoing amplitudes, and A and D are incoming amplitudes. So this unitarity condition, which is S dagger S is equal to 1, that implies that we can write this as S dagger S. So S dagger S is equal to 1. So what does it mean? Okay, so I can just simply write it as this S dagger S as S11 mod square plus S12 mod square, S11 S21 star plus S12 S22 star, and S21 S11 star plus S22 S12 star, and S22 mod square plus S21 mod square. Okay, and this, if it's unitary matrix, so this is S dagger S, and if this is a unitary matrix, then this is equal to 1, 0, and 0, 1. Okay, which immediately tells you that S11 mod square plus S12 mod square is equal to 1, and S22 mod square plus S21 mod square is equal to 1, and all these other things. So this is you can call it as equation number 1, and this as equation number 2. It's also true that the off diagonal elements are 0, which means that S11 S21 star plus S12 S22 star, this is equal to 0, and also the complex conjugate, which are S21 S11 star plus S22 S12 star, that's equal to 0 as well, and you can call this as equation number 3 and this as equation number 4. So these are the properties of the S matrix. These are the elements that follow these equations, and so on. If you subtract 1 from 2, then what you get is the following, that you have a S11 mod square minus a S22 mod square. This is equal to S21 mod square minus S12 mod square. This is equal to 0. And as well, which tells you that S11 mod equal to S22 mod and S21 mod equal to S12 mod. And the reason that we write it with a modulus is because these are in general complex numbers. Okay, so these are the terms, or rather the elements of the S matrix and their interdependencies that we wish to talk about. Okay, so let's look at the eigenvalues of S, which are of the form. So this eigenvalues of S are of the form e to the power I phi 1 and e to the power I phi 2, because these are in general complex numbers. So these phi 1 and phi 2 are real. Okay, so they are basically known as phi 1 and phi 2 are known as scattering phase shifts. Okay, so each problem in quantum mechanics, whether there's an incoming particle that's colliding with a wall or scattering against a wall means a potential barrier. These are all called as scattering problems. Okay, and these are the barrier transmission problems in its simple form. So these are the properties of the S matrix. The S matrix, the eigenvalues are complex in general, while these phi 1 and phi 2, which are real quantities, are known as the phase shifts. Okay, so let us assume that for a given case, for v of x equal to v of minus x, this means that the potential is even. Under parity. So what does it mean? It means that if you change x to minus x, v of x doesn't change, and you have seen this kind of potential for a harmonic oscillator, which is like half m omega square x square, right? So here v of x equal to half m omega square x square or half kx square. Now if you change the sign of x, because x square doesn't change sign, v of x will be equal to v of minus x. Okay, now in this particular case, the S matrix takes a form which are R, T, T, and R. We are talking about a single barrier. Barrier has, of course, two ends. So R and T are the complex reflection and the transmission coefficients. Okay, and we know that the reflection amplitude, which goes as mod small r square is equal to r, and the capital T is equal to small t square. Now this S11 mod square plus S12 mod square is equal to 1 is equivalent to r square plus t square, which is equal to 1, or r plus t equal to 1, which it has to be because the reflection plus the transmission amplitudes probabilities should add up to 1. And this is precisely the coming from the properties of the S matrix, which is this. This is the equation that I am referring to. Okay, this equation is it denotes r plus t equal to 1, capital R plus capital equal to 1. All right. So let us, given these conditions, let us assume that r equal to, without any loss of generality. So let's assume that this is equal to phi r. Because capital R equal to small r mod square, I'm taking, and small r is a complex quantity. So this is capital R is of course a real quantity. This it's root over r and exponential I phi r, where phi r is the phase corresponding to the reflected wave. And similarly, one can write down this relation, which is this is equal to t, which is 1 minus r and exponential I phi r. Okay, so this is the t. So unitarity further tells you that the phase shift under this transmission, the transmission and the reflection coefficients will have a phase shift which is pi by 2, which is coming from this e to the I plus or minus I, and if you remember, your I is nothing but exponential I pi by 2, because this is equal to cos pi by 2, which is 0, plus I sin pi by 2, which is equal to 1. Okay, so which means that this is equal to I. Okay, there's a sort of understanding. So that's why the R and T can be written as that. And now, of course, your S11, S21 star plus S12, S22 star, this is equal to 0, which is coming from this equation that we are talking about, which is coming from the off diagonal term of the S matrix. And from this, what one can get is the following, that one can get a RT star plus a TR star should be equal to 0. And in addition to these relationships, which we have, let me use another color, these definitions of R and T, we also have this expression, which is another relationship between R and T. Okay. All right. So now that tells that if I write these things properly using these relations above, then I get 2 of mod R mod T, which is equal to cosine of phi R minus phi T, that's equal to 0. That tells you, so this is equivalent to RT star plus TR star, and this is equivalent to a phi r minus a phi t. So this is equal to plus minus pi by 2 is what I have told you earlier, that the reflected wave and the transmitted wave will be phase different, will have a phase difference of either plus pi by 2 or minus pi by 2. Either it will lead or lag, and the transmitted wave will either lead or lag. Okay. Now let's take a specific example. Okay. Let's take a form for which is not too different than what we have talked about. Is equal to R identity matrix plus a T sigma x, where sigma x is a x component of the Pauli matrix, which is written as 0 1 1 0. Okay. So this is almost same as what you have seen earlier. So this is coming in as an example. Okay. So I'm trying to work out the entire barrier transmission problem in terms of the S matrix and the properties of the S matrix. This is quite sort of pedagogical in dealing with a variety of generic potentials, okay, which in terms of their reflection and transmission amplitudes. Now you know that each of these Pauli matrices have eigenvalues equal to +1 or -1. So sigma x has eigenvalues ±1. This is true with sigma y as well as sigma z. Okay, all have eigenvalues ±1. They have other properties such as each one of them square is equal to 1 for all I equal to x, y, z. It's not relevant here, but still let me tell you this: the determinant of each one of the sigma I is equal to -1, and the trace of each of the sigmas, sigma I equal to 0 for all I, and so on, and each one of them have eigenvalues ±1. So the eigenvalues of S is S is equal to either R plus T or R minus T. Okay, because of the identity, of course, identity matrix has eigenvalues only 1. So it's R and then either plus T or minus T. So if you define R plus T equal to exponential I phi 1, where phi 1 is a phase of that, and R minus T equal to exponential I phi 2, then from this R becomes equal to exponential minus I phi 2 and divided by 2, and T becomes equal to exponential I phi 1 plus I phi 2 divided by 2. So in addition to this, let us define a phi average which is equal to phi 1 plus phi 2 by 2, and delta phi to be phi 1 minus phi 2. In this case, your R becomes equal to, which is the reflection amplitude, which is equal to R mod square. It's equal to sine square delta phi, and T becomes equal to T square, which is equal to cos square delta phi. Okay, and to see basically how this makes sense, if you take phi 1 equal to phi 2, it means of course that sine square delta phi will have no reflection. So R is equal to 0, and the S matrix will take a form which is exponential I phi 1 and a 1 0 0 1 and so on and so forth. Okay, so this tells you that if there is no difference between the reflected and the transmitted waves, then of course, which means that there is no reflection that occurs, and the whole thing is transmitted. And we have used this. So this actually corresponds to a particular kind of potential where we have started with the S matrix instead of the potential and have calculated the reflection and the transmission coefficients. This is precisely what we have done while calculating the conductance of a junction, rather two junctions, and how those two junctions give rise to the conductance which is given by the trace of T dagger T, where T denotes the transmission amplitudes. Okay. Now this sort of gives you a sort of overall introduction about the conductance properties of a mesoscale systems, or in systems where you have there are ballistic transport and there are not much of inelastic collisions, so the system is small. And from here on, let's go and talk about the Hall effect. We'll like to start with the Hall effect and gradually want to go into quantum Hall effect, which is the main topic of our discussion. So how is this previous discussion related to this discussion? we are going to talk about conductivity either in Hall effect or in the longitudinal conductivity that one gets. That is, as you pass current through a material in the direction of passing current, there is a resistivity or a conductivity that develops, and if you want to measure it, this is the way to measure it, which is what we have learned in the last discussion that we had. Okay. Now, let's sort of talk about the discovery of Hall effect to begin with. Okay. And let's start with actually quantum Hall effect. So, we'll come to classical Hall effect that you all are familiar with in just some time. So, this is known very precisely, I mean, the discovery of this thing occurred in the night of 4th and 5th February 1980. Okay. And if you want to be precise about this, this happened at about 2 a.m. in the morning. The name of the discoverer is K.V. Kletzing, Klaus von Kletzing, and he discovered it, and in his notes on that night he actually said something very, very interesting. He said that he actually gave the resistance, which is the benchmark of resistance, and from this experiment which is done on particular type of semiconductors, two-dimensional semiconducting systems where the electron gases are mobile only on a plane, and from there he actually did the Hall effect experiment. This happened in Grenoble, France, and it happened in a lab which has facilities of large magnetic fields, and by large magnetic fields what we mean is about maybe 10 Tesla or even more, 5 to 15 Tesla, say for example. Okay, and how did he discover quantum Hall effect? The background story is that he has been working closely with two gentlemen called Dorda and Pepper, okay, who were engineers and who supplied samples to Klaus von Kletzing, and the samples to study the mobility of silicon MOSFETs. Okay. So, there is a semiconductor industry which was growing at that time, and it was quite important to actually get very high mobility samples. So, they were trying to increase the mobility of the samples, the silicon MOSFETs, and that is how it got discovered. These are FET devices, the field effect transistor devices, which were quite important to study in those days and still now. So, they supplied these samples, and Kletzing did the experiment, and Kletzing of course won a Nobel Prize for this discovery. And incidentally, I will tell you about the details of the discovery, and that will discuss throughout this course. This discovery occurred just about 100 years later than Edwin Hall, who discovered Hall effect. The Hall effect that you all are familiar with, the classical Hall effect, in 1879. So, 1879 and 1980 were just about 101 years apart, and that is where the interesting thing came. So, what is the difference between classical Hall effect and quantum Hall effect that we are going to study? The classical Hall effect is at room temperature, and it's at very low magnetic field, is less than 1 Tesla or even less than 0.5 Tesla that we do in our lab. I'll discuss that experiment that one does in the undergraduate labs of any of this institution or any of the teaching colleges or other institutes that one has. And it was found that this experiment by Edwin Hall very accurately measures the type of semiconductors from the sign of what we call as Hall coefficients, and it also gives a nice order of estimate for the density of the carriers. So the Hall resistivity, I'll just give you an example what Hall resistivity is, or the Hall resistivity, which is defined by something like so the Hall resistivity, let's call it as R, just R, which is equal to Hall voltage divided by the longitudinal current. And in fact, a more familiar quantity is known as RH. This is found to be like B over NQ, where B is the magnetic field and N is the density of the carriers and Q is the charge of the carriers, which of course we know that they are electrons. And there is a quantity which is more familiarly used, which is called as a Hall coefficient, which is R over B, which is equal to 1 over NQ, because we don't know whether the carriers are holes or electrons. That's why we want to leave it as Q. So this is one of the main findings, is that the Hall resistivity is proportional to B, which means that the Hall resistivity will grow linearly with B like this, okay. And this slope is nothing but it's equal to 1 over NQ. Now this slope, whether it's a positive slope or you have a plot which goes like this, that will tell you that the slope is has a positive sign or a negative sign, and this sign will decide that what kind of carriers you have, and the overall magnitude of the slope will tell you that what is N, that is the density of the carriers in that particular material or the semiconductor, okay. So this was the Hall experiment or Hall effect is all about. So let me try to make you give a feel that what actually is done in the lab. So this is a classical Hall effect setup. Okay, and let me make the drawing a little big and clear such that you are okay. So this is, say, a Hall sample. This is the let's call this as width as W. Now this is drawn not in scale. These samples are usually very thin samples, almost flat, close to 2 dimension, but I'm showing it with a width which is W. And let's say the this breadth of the sample is equal to D, and you send a current which is Jx here, and let me show the axis to be, this is X, this is Y, and this is Z axis, okay. So there is a magnetic field that is applied in this direction because this is the Z axis, and there is a current that is sent in this direction, that is the X direction. See the X direction in the figure, and now you want to measure the voltage in the Y direction, and that's called as the Hall voltage, okay. So this is where you measure the voltage by maybe a voltmeter or a multimeter and so on. Okay. So, this is the setup that you have, typical setup that you have in the labs that you. So, these the top and the bottom sort of planes are connected to a voltage measuring device, and this is so you have charges here. So, voltage measuring device, which is denoted by VH, which measures the hall voltage. Okay. So, what happens is that so there are these charges which experience low range force, and the low range force, these charges are moving because you are talking about almost like a free electron system. So, the force is given by Q V cross B. Now, your V, if they are moving along the x direction and then B is in the z direction. So, they are of course going to get deflected in the y direction, which is the vertical direction here. Okay. And I will sort of do a simple analysis now and then probably do a more refined analysis later. This is, I am just talking about a lab, how a lab, undergraduate lab would look at this thing. All right. So, at equilibrium, so what will happen is that all the charges will start migrating either in the plus y direction or minus y direction depending on their sign, and then you have these once the equilibrium is established, the motion of the charges will stop after that. Okay. So, what it means is that you have, so this is a there is a Q V cross B, that is the low range force, but there is also an electrical, so this is due to the magnetic field, there is due to an electric field, there is also a force which is proportional to or in the direction of the electric field. So, the total force on this is equal to F B plus F E. The electric field is because you are passing a current. So, you are, there is a battery that is connected, which I have not shown, but that is there, and that is why you have an electric force there. So, this is equal to Q into E plus V cross B, and this at equilibrium is equal to 0. Okay. So, understand that the charges cannot move due to these two fields indefinitely. Okay. They would eventually they would all the charges that are present in the system will either settle at the top plane or the bottom plane once the apparatus is switched on for quite some time, when the equilibrium will be established. Okay. V denotes of course the drift velocity of the carriers and so on, and then because of this there is a EY that is going to be created, because if you are measuring a hall voltage, there must be a electric field due to the hall voltage which must be created, which is equal to a VBZ, which is equal to Jx, which is equal to V. Let me write it with a capital J. So, this is equal to Jx by NQ, and B is only in the Z direction. So, I do not have to write a BZ. So, this is Jx by NQ and then BZ. So, what you do is that here N is the charge density. All right. So, the ratio, this EY divided by a Jxb, this is called as a Hall coefficient. And let us write it as with RH, H, capital H standing for Hall. Okay. And what we have shown is that this RH is equal to, so this is EY divided by Jx into B, this is equal to a VH D divided by I into B, where we have written the Jx to be the linear density of current, which is equal to I over D, because Jx was in the denominator. So, this is equal to I over D. D is the sort of width of this current, I mean this sample that you see here. Okay. So, from this equation, so this is equal to 1 over NQ, which is what I have said. From this is, it's very clear that this depends on the type of carrier density and also the density, the actual n, which is the density of the carriers. Okay. So this is the experimental setup and so on. So you how you actually apply the magnetic field, that's the question. Okay. And what you do is that you put the sample in presence or in between the pole pieces of an electromagnet, such that that direction, because if you put something in between an electromagnet, the magnetic field is going to penetrate that sample, and that becomes your z direction, which is shown here in this particular direction towards me. Okay. And then you sort of pass a current in a one of the other two directions, call that as the x direction, and measure the voltage in the third direction, let's call that as a y direction. So once you do that, and these electromagnets, as we have in the labs, in almost all labs that are having these experiments at the undergraduate or even at the MSc level, the magnetic field is not large, it's about 0.3 or 0.4 Tesla, anything between 0.2 to 0.4 Tesla and so on. So these magnetic field is applied so that the electrons they drift along the y direction, and you measure the voltage. Okay. So from the direction of the current and the magnetic field, one can estimate the direction and accumulation of the charge carriers in this y direction. Okay. And connect one of the voltage probes, that is Hall voltage probes, which is shown here. Okay. So that's a Hall voltage probe, and then such that you actually by connecting, say, a voltmeter, and so connect the other voltage probe to the other side of the voltmeter or maybe the ammeter, and leave this connection the way that it is. Now you record in this experiment, you record the voltages, record 4 sets of readings. Okay. And these readings are, you measure the voltage by this voltage probe or these Hall voltage probe, which is either a millivoltmeter or an ammeter and so on. So you measure it for a given magnetic field and current. Okay. Let's call this as V1. Okay. So let's call this BI, that is B applied in a particular direction, which is, say, the plus z direction, and I, which is along the plus x direction. Let's call that as V1. Now you change the direction of current, okay, by changing the pole pieces of the battery that is driving the current. Let's call that as V2. Now you calculate a minus B and I, that is, you change in the electromagnet, you reverse the pole pieces and calculate, which is known as V3, and then finally you have a minus B minus I, which let's call it as a V4. Okay. So this V3 is for the reverse field, and V4 is the reverse field and the current, and this is the reverse current and so on. Okay. So now using these data that you have in the lab, your VH in terms of this V1, V2, etc., can be written as V1 minus V2 minus V3 minus plus V4 and so on. Okay, and divided by V1 minus V2 minus V3 and plus V4, and so this is the expression for the Hall voltage, and you note down the Hall voltage, and once you get the Hall voltage, you can put it into the formula that had been discussed, that once you get this Hall voltage, you know the current and you know the dimensions of the system, which is D and I, and you also know the magnetic field, so you can get RH, which is nothing but 1 over NQ. Okay, and you repeat the measurements with whatever values of magnetic field and current that are available to you, and usually the width of the sample, that is D, is of the order of is about maybe around 5 mm, and W is very small, this is around 0.5 mm. Okay, so this is the or the length of the sample, and the width of the sample, which is the thickness of the sample, so to say, is 0.5 mm, which is these are samples that are available, and now you can draw suitable graphs, and as a function of b and VH, and then you can actually calculate from the slope, what are the sign of the charge carriers, that is whether they are electrons or whether they are holes. And the fact remains at the end that your RH or R is proportional to B. So the R versus B is a straight line, is what I mean. Okay. Now, when von Klitzing did this experiment, he found something very unusual, and this unusual things gave rise to a lot of interesting phenomena. He found that the Hall resistivity, we'll write it as R or we'll write it as rho, it has a structure like this. There's a very rough drawing, but and so on, and then this, there is a bit of so this is as a function of B, and the experiment is done at, I'll show you better pictures of this, but right now it's just a schematic drawing. And why did I not show this kind of step like structure? Because this is the region where the classical Hall effect is the experiment is done at very small b, where it's almost like a straight line, okay, which I did not show, of course. Showed it with a freehand drawing, which is and just to show that there is no plateau structure there. So this plateaus actually threw a lot of surprise, and why should there be plateaus, and what happens, which means that the Hall resistivity doesn't increase in this region as you increase the magnetic field. You have to understand that why should Hall the resistance would increase with the magnetic field. Okay, a very simple sort of calculation would show you this, that when you change the magnetic field, you actually change the carrier density. And how you change the carrier density? You change it because this is like 0 to mu, so this is your carrier density is equal to some f of E, g of E, and d of E. Okay, so this E is the energy of the electrons in presence of a magnetic field. Okay, we don't know as yet what that is, but this is a general formula. This is for the density of electrons, or is the total number of electrons. Okay, I mean you can write this as total number of electrons because you have integrated the density of states. So either I write n, and then somehow if I divide it by V, that is will become the density of carriers. So in that case it becomes n. Now this is some function of E, which sort of this includes a magnetic field. So this is the Fermi distribution function. To remind you, what is the Fermi distribution function? The distribution function is exponential beta epsilon minus mu plus 1, and so this is the bare electron, where electronic energy levels are written as h cross square k square over 2m, and mu denotes the chemical potential. Here this mu is the chemical potential, and this is the density of states. Okay, so because every quantity, physical quantity that you would like to determine depends on the density of states, that how many states are there. That tells you what the properties will be and how the properties are different in different dimensions. Okay, and because this density of states have different behavior with energy, and we are really looking for energies close to the Fermi energy for most of our conductance behavior. Okay, so this tells you that as you sweep B or as you increase B, we told that you put things inside an electromagnet and take reading for various B's, which means that you make the current that is flowing in the electromagnet to be larger and larger, so that you can actually sweep over a range of magnetic field. There it was very small. You start from 0 magnetic field and go up to maybe 0.4 Tesla, whereas here you go up to maybe 10 Tesla or 15 Tesla, which is a large magnetic field. and these distribution function will be proportional to, not really proportional, but it will sort of scale as you change the magnetic field, because of the reason that this quantity, the Fermi distribution function, will be a function of B, because it will enter through the energy. I wrote it separately, but doesn't mean that we are talking about these two will scale independently. They will depend on each other, and this will increase as you sweep B, as you make B to be larger. When that happens, then the conductivity will be different. Okay, it will change, just like in the classical Hall effect. We saw that as you change B, this resistivity, or the Hall resistance, so to say, that scales with the magnetic field. Here also you should do that. But why is this region, this plateau region, coming? And because of this plateau region, these are called plateaus. And because of this plateau region, the name had come that it's a quantized Hall effect or a quantum Hall effect. Because here the resistivity is not just a monotonic function, linear function of B, but it shows plateaus, and these plateaus are interesting. Now, what Klitzing found out on the day of his discovery, in which he actually wrote some nice notes, they are sort of illegible because they have been used many times, but he had found out that these resistivities are quantized in h over e square, which means this has a value h over e square. I am just giving you an example. This is h over 2e square, this is h over 3e square, and so on. Okay, so these are happening. These now these are resistivity, so they have, so this value is h over 3e square, this value is h over 2 e square, and this value is h over e square, and so on and so forth. Okay, and he found that this has a value which is, it's 25.813 kilo ohms. Okay, and this is a resistance which is now taken as a unit of resistance. Now you see that H is a Planck's constant, okay? E is the electronic charge, and these two put together define a unit of resistance. These are quantum mechanical quantities. Like H sets the scale of energy. If you remember that E equal to H nu or H cross omega as appeared in Planck's theory of radiation. So this is the quantized energy of the photons, with the H having a value which is 6.63 into 10 to the power minus 34 joule second. And this H was initially introduced by Bohr's theory of atoms, where the electrons have angular momenta which are quantized in unit of H, such that when they move around in the stationary orbits, they do not emit electromagnetic radiation, and these are called as the stationary orbits. Okay, and E is the electronic charge, which has a value 1.6 into 10 to the power minus 19 coulomb. Thus, all these microscopic quantities H and E, they put together define the unit of resistance, which is H over E square, which is a measurable quantity, and it comes out in the Hall experiment. Okay, and this is known as metrology. What it means is that metrology is this scientific study of measurement which establishes a common understanding of units in the context of this modern manufacturing industry. Metrology also refers to the calibration of machines that are used in the production process. And for example, defining the length of an object, one uses the laser interferometry. So here we define the unit of resistance, or we fix resistance by this experiment. And this experiment, think of this, it is done in the lab. Okay, of course we are talking about low temperature and large magnetic field, but they are still accessible. Low temperature is we know that liquid nitrogen temperature or liquid helium temperature, if you want to go to still lower values, like liquid helium temperature is about 4.2 Kelvin and liquid nitrogen is about 77 Kelvin. These are low enough temperatures for a specific kind of experiments. I mean, you probably need to go to farther lower temperatures to see some other effects. Let's not go into that, but here it's an experiment that's done with samples which are not perfectly clean, which we'll see in the coming discussions, but they still are able to fix the value of the resistance. This is the one of the main triumphs of the quantum Hall effect, which was missing in the classical version of the Hall effect, which could only give you, for a given sample, which could give you the sign of the carriers, that is whether they are electrons or holes, or what is the carrier density for that particular sample, which could be anything between 10 to the power 16 to 10 to the power 19, but it does not say anything which is a fundamental quantity. Now, this tells you about a fundamental quantity. If you see that it has the really the resistance, the unit of resistance H over E square, and we'll also, in almost a similar manner, we'll talk about conductivity, which has a scale which is inverse of that. So, this is called as conductivity. And conductivity is either written in ohm inverse or it is written as mho, MHO. So, this omega is called ohm and this is called as mho, just the opposite. Okay, so, that is called as a conductance. So, I hope, just to put things in perspective in half a minute, we have done a thorough calculation of conductivity in nanostructures or mesostructures, mesoscopic quantities, rather systems, the mesoscopic scales of those quantities. And then we came to talk about Hall effect, which is not, we are not interested in calculating the longitudinal resistance, which of course we also would be discussing longitudinal resistance, but here we are more interested in talking about the transverse resistance, that is perpendicular to the direction where you send the current, you measure the voltage in a direction which is perpendicular to that. That's called as a Hall voltage. So, the system, or rather the formalism doesn't change, the system also remains the same, excepting that we are talking about a different resistance and a different resistivity of the material, property of the material, and the property very convincingly shows us the resistivity to be a universal constant, and 25.813 kilo ohm corresponds to the value H over E square, which are known to be purely quantum mechanical quantities. Okay.